It's still nice outside, so I mean, I have no objection if you want to leave now. But also, I'm really excited. This is the first time I'm using a. Fantastic. So you can go fast, you can go slow. Yeah. Okay. Okay, so it's about expansion, and there will be an SDP in this talk, and some other things. It's joint work with Anand Lewis, who's now at Princeton, and Prasad, who's here. Okay, graph expansion, just to get my notation down. A graph with weights on the edges, non-negative. For any subset, you look at the total weight of edges leaving the subset, divide by the total weight of edges in the subset or its complement, incident to the subset or its complement, and that ratio is the expansion of the subset. And then the minimum overall subsets of the vertices of the graph is graph expansion. Edge expansion. It can be hard to compute exactly, and it admits square root log n, constant square root log n approximation, which improves the earlier log n approximation of Leighton Rao and okay, great problem. Now this other view, the spectral view of adjacency matrices, you could have general weights, normalized so that every row sums to 1. Laplacian normalized again, so it's just identity minus this normalized. Adjacency matrix, convenient, you know, the smallest eigenvalue is 0, and the second one is this quadratic form, which you can interpret as the minimum overall vectors orthogonal to the degree sequence of the sum over all edges of the weight times the difference squared divided by the sum over all vertices weighted by the degree. Okay, it's clearly non-negative, so sum of squares. Okay. Perron and Frobenius says lambda 2 is 0 if and only if the graph is disconnected. I've seen this times. And if it's close to 0, then is it close to disconnected? So Cheeger answered this, Cheeger, Alone, and Willman, saying that in fact it's at most square root 2 lambda 2. Why? Let's see one direction. So there are two inequalities here. This is the definition of lambda 2, no change. And now we relax. I added this term which is 0 because x is orthogonal to d. And now let's restrict to only 0, 1 vectors, so which specify subsets. It can only go up. And now if you interpret what it means, the subset, so x is the indicator vector of some subset, you end up with the weight of the subset and the weight of its complement. And that's at most twice 5g. Okay, because one of them is half the weight of the graph. Okay. Now, Cheeger's algorithm for the other inequality, take the eigenvector for lambda 2, sort it according to its value, the coordinates, and then take subsets that are consistent with the sorting. So prefixes of this. Of those, take the one that has the smallest ratio, smallest expansion. And this gives you square root 2 lambda 2, and really the only inequality used in the proof is Cauchy-Schwarz. There are now very nice alternative ways to interpret it. You can, for example, say pick a random number r between 0 and 1, and then you see whether you take as your subset all the i's for which xi squared is less than r. And that also gives you a similar bound. Okay, so I won't do the Cauchy-Schwarz proof here. But one nice thing here is that it gives a method to certify constant edge expansion. So if the expansion is alpha, you get a certificate that it's at least alpha squared. Okay. Okay. It's very useful in applications and in theoretical work. Yeah. Maybe it's Not something that you'd find in a chapter in a graph theory book, but I think the next graph theory book will have it as a feature. Okay, so here's what I want to do in this talk. First, vertex expansion, which is, instead of counting, we'll define in a minute formally, instead of counting edges leaving the subset, you want to count vertices. How many vertices are near a subset? And how can we approximate it? And can we certify constant vertex expansion? Then hypergraphs, right? So not just pairs, but subsets are edges. What can we do there? What is expansion, and are there such inequalities? And then whatever bounds we know and we can get here, how far are they from the best possible? So that's the. Okay, so vertex expansion is you can define in a few different ways. I'll use this symmetric version. So for a subset, you're counting the number of vertices in the subset that have a neighbor outside and outside the subset that have a neighbor inside. Sometimes you do the outer only, sometimes you do the inner only. We do both. These are all equivalent up to constant factors for approximation purposes in polynomial time. Okay, so that's the. Now I've removed the weights for simplicity. You can do all this with non-negative weights. So, and we'll also assume that it's a regular graph for this part of the talk. So again, that makes more notation, but it doesn't change any of the ideas here. So the minimum vertex expansion is the expansion of a subset for which this ratio is minimized. That's the vertex expansion of the graph. This is also a fundamental parameter, and there's lots of applications. And also has a square root log n approximation with a different method that uses, at least the one that first gave the square root log n. That's a different method. Now, if you use the second eigenvector, so if you use the Friedler vector, then you get something that grows as square root of the degree times lambda 2. Okay. And this is already in Alon's paper. So, if the degree is constant, then these things are within constant factors, the edge expansion and the vertex expansion anyway, and of course the bounds also. But what if the degree is a parameter that's growing independent of whatever approximation you want? So here's a question. I have a graph. It's a vertex expander of expansion, let's say 0.1. Can you certify that its expansion is at least 0.001? Okay, so I want a polynomial size proof that its expansion is at least 0.00. You can do this for edge expansion. So what should we do? Sorry, I went.
Should you think of the degree, the interesting degree, as being what log n over 2 square root n? Like what's the?
It's just something growing independent of lambda. Okay. So you'll see what the bounds are in a minute. For now, it's a separate parameter d. So it's just independent of lambda and n and yeah. We'll give a bound based on the degree that works for any degree, but yeah. Okay. Okay, so here is a way to formulate, this is an equality, the same thing, but I'm writing it as an integer program or an integer ratio. The denominator is the same as you have in the edge expansion case. It's just counting a subset. Basically, if x is the indicator vector of a subset, this is essentially counting the size of the subset times its complement. But the numerator, what we're doing is that for every edge, for every vertex, you see, is there an edge crossing or not? Right? So for every I, you look over all j and check, is there at least one edge going across? And if there is one, at least one of these terms will be 1, and you only count the max. So you count once for every vertex that has something outside, something on the other side. Okay, so this is a symmetric vertex expansion, right? It's going to count for every vertex 1 if it has a neighbor on the other side. Okay, so that's exact. And I just wrote the same thing. And so it's not the min, you get the product divided by n in this formulation as usual, but that's just a factor of 2 off. So this part of Cheeger's inequality, no problem, at least with this definition. Of course, the question is whether we can compute it. As it is, I mean, these are all subsets, so no, not efficiently. So let's relax it, just like you do in edge expansion, you relax to get a solvable, polynomial time solvable program. Now, when you relax it, Same relaxation, we're just going to real vectors instead of 0, 1. And since I assume constant degree, it's orthogonal to 1. Since because it's orthogonal to 1, I can drop the subtraction term. And here is the formulation. And Bobkov, Udre, and Tetali, who defined this parameter, as it is here, proved that this parameter, in fact, can be thought of as giving a Cheeger inequality. This one, it's from the definition. We just saw it. This takes some work. We'll see in a minute. So it's not square root 2, but there's some constant here. Okay. So that then raises the question: can you compute this? Is this an effective approximation? Okay. So I think everybody in the audience knows what to do next. Let's say it together. 1, 2, 3. SDP. Come on, guys. 1, 2, 3. SDP. Was I tried? Okay. So here, it's already written there. Okay. I thought it was hot, but I guess. Yeah. Okay. So anyway, here is the thing here. You can still leave. I'm sorry. Here it is. So so you just symbolically replace the xi's with vectors instead of real numbers, and the squares with squared norms. That's okay. And instead of forget about the orthogonality constraint, we'll put back the subtraction term. And since we relaxed from real numbers to vectors, we get something that can only be smaller. We're minimizing, so it can only be smaller. So it's smaller than this lambda infinity. And you can compute it, right? It's just an SDP. Using only inner products. Okay. So,
What about the max?
well, it's just a linear constraint, right? So this is a linear term so let me just take one more step. So what are the variables? The variables are the inner products xi dot xj. So this is a linear function here. So linear here. So for each vertex I, let's put a variable that is at least the distance for all the
alpha I such that alpha I is larger.
Alpha I is larger than what you get for each vertex, for the vertex I. Right? So this you turn into a linear constraint. You have a linear objective function, and this is also another constraint, and you minimize this.
I was going to say, use one of these softmax functions. Why don't you do that instead? For the max.
I see. So do a summation. And, well, you don't have to.
Like e to the blah, blah, blah.
Right. Yeah, so.
You know how they do this in
that sounds.
These guys, multiplicative weights, sort of. You know what I'm saying?
Yeah, sort of know.
Anyway,
Yeah. So you're saying why max? Why hard max? Why not do some kind of exponentiated combination of these?
Softmax is all these kids are using these days.
Which ones? Find them out.
I don't want them.
Okay, so I don't know. Maybe you can. This is already convex,
Okay.
right? I mean, this is already convex, so why not? So I don't need to do anything further. This is already exactly up to arbitrary accuracy solvable thing. Okay. And now here is the theorem. You have lambda. This we already showed by definition. Now this is a relaxation. So what I need to show is, so this SDP is also a lower bound. It's sitting over here. Sorry, I should have written one more line. SDP is smaller than this. Now this will recover a cut, which is at most square root of the SDP solution times log d. Not the d that you get from Cheeger, but log d. Edge expansion Cheeger log d. And of course, since SDP is lower than lambda infinity, it's square root lambda infinity. So the approximation is order square root log d. Okay. Now, so what's the algorithm? It's you solve the SDP. Okay. You have these vectors. Pick one random Gaussian vector. And this could have been discovered before max cut. It's of the same complexity. Pick one Gaussian vector, project onto this Gaussian vector your vectors, so you get a sorting of the vertices. Consider cuts in that order, basically the Cheeger sweep. Go use prefixes in that order, take the best one with respect to vertex expansion. Or the modern view, take a random threshold cut. That's it. Right, that's the algorithm. So you solve the SDP, you have n vectors, you project onto a line, and then you consider all the n cuts. Okay, so really all I have to show you is that after projection, your value didn't go up much. Because after that, I can just use Bobkov Udre-Tatali, who said that given a vector, it goes up by, what you recover is square root of that, times the constant. Okay. So they don't state their algorithm like this, but in fact, it's embedded in there. So, okay, so all you need to see is this inequality, right? And what is this saying? It's two things that are concentrated near their expectation. This one just doesn't even have any max or anything. It's just a summation. The yi's are what? Gaussian times xi. So it's just itself the length squared of a Gaussian. It's concentrated near its expectation. What about the numerator? Well, each of these terms is just concentrated near its expectation. But there is a max. But a max of how many things? Only d things. So you will lose square root log d, and in the square you lose log d. Sum it up, that's just a sum, so you lose nothing, and that's log d.
And this is really where the loss comes in.
Yeah. That's it. This is the rest is constant. I mean, you lose the square root, but that. Okay. So that's.
So then, could you improve it with all these kind of things that James is doing, like Gaussian processes and these kind of things? Or?
That would be very nice. So I try to give you a partial answer. But before we do that, it seems simple enough. Let's generalize it. Okay, let's. Why not? So hypergraph expansion. Well, the motivation is that you want a common generalization. We have the same algorithm for both almost. You have a vector and you do a sweep. Why not find a common generalization of two problems that look like two different problems? So here is hypergraph expansion. And what is hypergraph expansion? You have edges which are now subsets instead of pairs. And the expansion is you have a subset of vertices and you count how many subsets, how many hyper edges have at least one vertex inside and one vertex outside. Okay? So that's the hypergraph problem. You have a hypergraph, you have a subset of vertices, and for each hyper edge, you count all the ones. If they are weighted, count their weights, which cross this boundary, which means we have an intersection with both sides. Okay. So that's the definition. And you can see that this captures both edge and vertex expansion. In the edge case, it's just trivially the hyper edges are the edges, so edges cross. In the vertex case, you define the hyper edge as the set of all neighbors of each vertex. Those are the hyper edges. Yes?
Doesn't that create a problem about, as in two neighbors, as in that would qualify as a cut here, right? That's not necessarily true in vertex expansion.
Sorry?
When you...
I have to define the hyper edges for vertex expansion. I have to define a graph for which we'll apply this.
I thought you just said it's a neighborhood, right?
Sorry? Yes, for each vertex, it's the neighborhood. Right? That's the hyper edge.
Right.
So you'll count it once. You count it once if it crosses.
No, but so here's the question. So if...
Yeah, 2, factor of 2. So you might count from both sides.
No. But if in the whole neighborhood, if just two neighbors are on the other opposite sides of the cut, then you count it for it gets counted for every vertex in that neighborhood.
But you're creating only one hyperedge for this vertex. So here is the formula of the max formulation. For each hyperedge, you are again looking at whether there is at least one element of the hyperedge. Now this E represents a hyperedge instead of an edge, right? It's a set of points. So checking for each hyperedge whether it crosses. This value is 1 only if it crosses. It's the same formulation as before over a different set of subsets.
Now we're doing the analog of edge expansion.
Both. Exactly, edge expansion, but it captures vertex expansion on the hyperledge. Yeah, exactly. Yes, exactly. And then now, why not define a parameter which is an SDP, the same SDP, except the set of constraints instead of being 1 for each vertex, now it's 1 for each hyperedge, and you get this using the same same method as Bobkov-Wood-Ritatelli for this parameter. And in fact, you can approximate this to within log R, where R is the maximum size of a hyperedge, because you have to take the max over R Gaussian.
Oh, no, I'm sorry. So there we summed over vertices.
Yes. Here, a hyperedge, these are hyperedges. A hyperedge corresponds to a single vertex. I'm defining one hyperedge for the neighborhood of each vertex of your original graph. Okay, so you get this to within log R. I mean, this is almost a symbolic change to the proof. Now, Anand Lewis and Makarichev have shown recently that with this formulation, they get a square root log n approximation if you also add the L2 squared metric constraints. So you take this SDP, add the L2 squared metric constraints, you get square root log n, which means that you have one algorithm now, and the rounding algorithm is ARV. You have one algorithm now for edge expansion and vertex expansion. You don't need, these spreading constraints and so on, which you previously used for. Something useful is coming. Now, I want to say a few more things about this because it seems interesting. So this is the basic continuous parameter. One nice thing about edge expansion is that the parameter corresponds very closely to this random process, a random walk, according to the weights of the graph. And so for either, you can keep in mind vertex expansion if you prefer, or hypergraph expansion. Is there a random process that matches this parameter? The simple random walk, the rate at which it converges is exactly lambda 2 for edge expansion, lambda 2 of the. What about this? Is there some process? And so here is the process. Start with some distribution on the vertices. Okay, so at any point you have a distribution of vertices, so that's the current distribution, and we're going to make a change on it, a local change. Normally what you do, you look at, you basically average over the neighbors. That's the normal random walk. You go to each neighbor with probability proportional to the edge. Here, you pick a random hyperedge. You look at the largest difference, the pair of vertices that have the largest difference. So if you stick to vertex expansion, you pick the neighborhood of a vertex, including the vertex, and you see which neighbor has the largest difference with it. And you make a little transfer of mass between those two. Only 1 over 2d times the difference between the two. So whichever are where you see the maximum discrepancy, you transfer some mass. That's the process.
What is D?
D is the degree. So I'm assuming constant degree right now. But it would be
It's a deregular hypergraph.
deregular hypergraph. So D is R for the hypergraph case, sorry.
So it's the size of the average.
The size of the hypergraph. Not the number of hypergraph, it's the size of the hypergraph. It's the size of the hypergraph.
D uniform.
D uniform hypergraph. DR, sorry, this should be R since I moved here too. Okay, so if you think of this as a process, this step of updating X, it's some process that's updating a vector X.
Wait, actually, sorry. So the previous operator you defined, when you're incrementing by xi minus xj divided by that, is that I'm a little confused with the D's and R's.
D is equal to R.
Is it the size of the hyperedge, or is it the regularity of the
Size of the hyperedge.
The size of the hyperedge.
We don't need the regularity of the hypergraph, we just need the size of the
Should
hyperedge.
be R there for the
Yes,
setting? Okay.
yes. For the vertex expansion, R is D, but yeah.
Okay. Yep.
Yeah. So there is a vector X, the current xt. We apply this operator, which picks randomly each hyperedge, and then it makes this transfer of mass, and that gets you the next vector.
So are you doing it actually in parallel for all the averages?
Just like you think of as random walk, right? You're updating the probability distribution. Each vertex decides what with the current probability, it decides where to go.
So
in the next step.
simultaneously.
Exactly. So it's like in the normal random walk, it's just a linear operator. You take the transition matrix and apply it to the current vector. Here it's not linear, it's something, but it gives you an exact rule how to do it. Okay. So does this converge? To what and at what rate? And Anand Lewis proved that under some mild conditions, these are basically what you require even in the edge expansion case, like should not be bipartite and it should be connected and so on. The process will convert at the rate 1 over gamma 2. This is this continuous parameter we defined, and to a vector which is stable under this operator. Of course, that's what convergence means. That when you apply this operator again, it doesn't change. Okay, but this is gamma 2. Just to remind you, we can rewrite gamma 2 like this. because this is now an operator that's capturing the max and all that.
So just a second. Gamma 2 is this thing that we don't know how to compute, right?
Yes. We don't know how to compute.
But
except
we don't know how to run the process.
We know how to run the process. Gamma 2 is telling you the rate at which the process converges.
So we did know.
Well, I mean, not efficiently necessarily, right? What if gamma 2 is very small?
Can it be exponentially small?
I think so. I mean,
But
How
I
could it be?
I guess
Wait
the
a
reason
minute.
you don't know it is that you have to start.
no, wait a minute. Sorry, yeah.
When it converges at that rate, that means that's like the worst possible convergence rate, right?
Oh, yeah.
Right, we don't know the worst.
We don't know
the
Right, that's the point.
So you can't you just pick a random x and try and measure the rate of convergence. It might not.
What do you mean? For normal random walk, the rate of convergence actually is lambda 2.
Yeah.
Doesn't matter where you start.
What about hypergraph? It's lambda 2 if you start from the worst possible initial condition.
Yeah.
I mean, this has to be the point, right? Because
Right.
otherwise you could compute it. Or
Yes. So this is a bound on the rate. At most 1 over gamma 2. Yeah. Well, it's still not clear to me that otherwise you can compute it because you have to actually measure the changes.
It actually does give you, like, if you run the process, maybe in some sense it does give
Give
you
it to a
some kind
bound.
of relaxation, some kind of, I'm getting confused, lower bound or upper bound, some kind of bound on gamma 2, which may or may be worse or better than the SDP, some kind of approximation.
Yeah. So, okay, this is a process that, I'm really putting this up because, you could define 1,000 different processes. And this is one that matches the particular parameter we defined because of the max in there. But I don't know which ones are interesting, which ones are computable. Okay, I don't know what else to do with this. It's not clear that computing it is the most interesting question right now. But it's certainly... Okay.
Wait, so if you found the x that minimizes this, would it give you square root without the log?
Exactly. Constant square root. Yes. That's yes. Exactly. Yeah. I mean, whatever x you have, you can look at its value as if it's a Rayleigh coefficient, and you get square root of. Okay. So, question is, can you do better than this log d, square root log d, so on? And more precisely, can we approximate in polynomial time edge expansion to better than square root opt, right? Which is what Cheeger gives you. Vertex expansion to better than square root of log d, and within this, maybe a very important special case is, can you certify vertex expansion is at least some constant in polynomial time, and then hypergraph expansion to better than square root of log r. So these are the bounds other than the span. This is what we can get right now up to constants, and can you do better? I mean, this question motivated a lot of developments over the past decade. So. And this has an interesting extra parameter. Maybe it's easier to prove, right? Something, because the problem is harder, maybe. Okay, so let me remind you of the first talk from the second day. Which,
The second talk from the first.
we can play a game, actually. That sounds great.
Yes. Let me remind you of minute 17 and like slide.
For those of you who were not here. Okay, so here's the problem. Given a graph, another expansion problem. Not just another, okay. You have to distinguish between two cases. So it's a problem of deciding one or the other. Does there exist a subset of measure? You can make this at most a delta fraction of the vertex weight, so that its edge expansion is at most epsilon. Epsilon is part of the input. Or is it the case for every subset of small measure, the expansion is at least 1 minus epsilon? So those are the two things you have to distinguish. And these guys conjectured that this is NP-hard. I think it's ridiculous myself, but they conjectured that it's NP-hard. Okay. But ridiculous things are fun to work on, right? I mean, it's great. Yeah. So okay.
Find the polynomial algorithm and be done with it.
I know. Yeah.
Let him get to the end of the talk.
conjecture is NP hard or just that it's hard?
Well, I mean,
It's
Like
it's not really the same like the unique.
no. The conjecture is NP hard, yeah. I mean, there are precise parameter values for which, but yes, just like unique games. And it turns out that this is, I shouldn't say, this is an easier problem than unique games in the sense that if you can solve this problem, you can solve a unique games instance.
Never.
Never get that wrong. Okay, so it's easier than unique games. Am I right?
Yes.
Yes. Okay.
I was reading an article, because Subhash got the Nevelino award.
Yeah.
He only says, well, it's probably in between.
Right.
He may be in between, so he's not sticking to NP hardness.
Right.
Yeah.
Let's see. Last time I talked to Subash, he actually still NP. I think it's NP hard.
Okay.
He still tries to prove it. So yes.
So yeah, this would be even harder to prove NP hard, but it's there. Okay. So I don't know. I mean, you just want to distinguish expansion by a huge factor. That's okay. So here are the theorems. Let's assume this now. It's very. We don't know. Right now, there is no polynomial time algorithm for it. There is an algorithm that does it in sub-exponential time, Raghavendra-Steurer, for this problem here. So it's not 2 to the n. It's 2 to the n to the epsilon, small epsilon. But sorry.
Same epsilon.
Yeah. I guess order or whatever. But there's nothing close to polynomial. So what quickly followed their conjecture, the Raghavendra-Steurer conjecture, is this paper by Raghavendra-Steurer Tulsiani, which showed that assuming this hypothesis, edge expansion is in fact hard to approximate to better than what Cheeger gives you. Up to constant. So Cheeger gave you square root up. You can't do better than that if this is actually hard. So basically, you need to solve this problem if you want to do better than square root out. Which is a great way to focus, right? So, for expansion, we have basically no lower bound, right? I mean, we cannot prove 1.01 hardness. We cannot prove hard for n to the log n. What we managed to do is that for vertex expansion, in fact, it's square root of log d. This is the upper bound I just showed you. So if you want to do better than this, you better do better on small. And as a result, in fact, it's hard to decide if a vertex has, so this is just saying if a graph has vertex expansion less than epsilon or at least square root epsilon log d, so you cannot actually certify constant expansion of a constant vertex expansion unless SSE is false.
So it means your parameter gamma 2, it's hard to approximate within log d.
Square root gamma 2 within log d, yes. Better than log d, yes. Okay, so how does this work? This is sort of a path that has been laid out over the past decade for several problems, and I will sort of sketch some of them and show you some of the new parts of this in the remaining 10 minutes. So you start with an instance, right, where you want to solve this expansion problem. We're going to show that, look, if you can do vertex expansion to better than, if you can distinguish vertex expansion epsilon from square root epsilon log d, then you can solve the SSE problem. Okay, that's the ultimate conclusion. So on the way, some nice things happen. This step I've basically skipped for this talk completely. We assume we're already interested only in symmetric vertex expansion. You lose a constant here. Balanced vertex expansion is the same as vertex expansion, but you're only looking at vertex expansion of subsets of measure at least constant fraction. Okay. So not the vertex expansion of the entire graph, but only subsets of at least. This could make it harder or easier, but okay. But in fact, if you can do this, you can do it the general case and so on. So these two steps are basically graph theoretic reductions. Now in this paper we define an intermediate problem which is called balanced analytic expansion. I'll define it in a minute, and that will be the link between small set expansion and vertex expansion. Okay, so what is this balanced analytic expansion? So you have a set of vertices V, which could be an infinite set, and you have a probability distribution over d plus 1 subsets of size d plus 1. Okay. So there is some distribution specified over subsets of size d plus 1. So if it's an explicit hypergraph, maybe these are a d plus 1 uniform hypergraph, then it's just say uniform on the hyperedges. But it could be something over. And this will also have a marginal on pairs. Okay, so if you have on subsets, you look at what it induces on pairs. Okay. And so what is this quantity, this balanced analytic expansion? First we define analytic expansion. You look at the expectation over this distribution over subsets for 0, 1 functions. So these are specifying some subset of vertices. This is a familiar term here, right? It's looking at the difference between yi and x, the function value. Are you different? Is the function different? But you're only looking at a tuple that was picked from this distribution. So it's a distribution on d plus 1 tuples. You pick a tuple. The first one is special, the first one in the tuple. And you look to see whether the difference in the function between the first and any of the rest is large. Whatever is the largest, that's what you count. Denominator, you're doing the same thing, but you're just looking at pairs from the marginal distribution. So denominator simply counts the size of the set times the size of its complement. That's all the denominator counts.
So P1 is the distribution over single vertices, and x and y are picked independently from
No. P1 is the distribution over pairs induced by this distribution of tuples.
And what do you mean by induced by? That you pick a d plus 1 tuple and then you pick 2 random elements of it.
Exactly.
So we can think of the distribution. So we can think of the distribution already as a hypergraph. So this looks kind of directly like hypergraph, what you define as hypergraph expansion, right?
Yeah, almost, yes. Yes, it looks very much like that. It looks very much like
weighted hypergraph.
Right. And I made it a bit more general by saying it's a distribution on tuples and so on.
Distribution of tuples is a weighted hypergraph.
Yeah, exactly. Yeah, fine. That's a discrete version, but we'll in fact pass to a continuous version, but that's okay. Okay.
But for d equal 1, P1 would just be equal to P.
Yes. Yes, that's right. So for d equal to 1, you get edge expansion.
These are over pairs?
No, very good. Let's take d equal to 1. It's a good case. D equal to 1. You get pairs, right? So you're counting if it's different over the edges of the graph. Oh, you're right. Sorry. Extremely. Thank you. So
P1 is on the
vertices. P1 is the marginal on vertices.
Yeah. So you take two independent.
Yeah, you're right.
It's like you're weighing vertices.
Yeah. P1 is just the marginal vertices. You pick a hyperedge and pick a random vertex from it. Whatever the probability of the vertices we have selected, that's P1. Okay. And so to do this, you pick x and y independently. Okay. Yeah, you're right. Thank you. Yeah. Okay. And so we want balanced also, which just means that we enforce that when we pick a pair of vertices, your value is at least one. You're picking balanced. The function is balanced. So I generalized edge expansion because d is 1, as just remarked. And we will now reduce from small set expansion to this problem, which is starting to look like vertex expansion already, right? And hypergraph expansion. So actually, and the reduction in the main steps follows what was done to prove the square root opt lower bound in Raghavendra-Steurer. So but let me first show you the second part, which is from here, how do you go to vertex expansion? That's the easy part. It's just Hofting bound. So what you do here is, you remember this is the quantity. You sample a vertex, sample neighbors, and this is basically asking what is the probability that at least one y lies outside the subset. Right? Because then it's counted in the numerator, otherwise it's not counted. And as we were saying before, with d equal to 1, it's the edge expansion, and if you make d is infinity, that means you're looking at all neighbors, you get vertex expansion, the max over all neighbors. Now, in fact, computing this quantity implies that you can, reduces to computing the vertex expansion in graphs with degree order d. Why? Because we have this distribution. We'll just sample a large enough number of tuples from this, fix a hypergraph, and run vertex expansion on that hypergraph, and it will approximate this value. Okay, so we just need to show that for every function, you are truthfully represented up to a small approximation. Yeah. So that's what I meant by Hoeffding bounds. So now we focus on reducing the hardness of this problem. So this is the reminder. So basically, I sketched from here to here. Now we need to do this here for the balance. So this is the outline for how you take an SSE instance. So you have a graph, and you want to check, is there a subset whose a small subset whose expansion is less than epsilon, or for every small subset the expansion is almost 1. That's the instance. And the point is that you have this gadget, which is a tiny graph. In all previous papers, it was a single edge, I think. Now in our paper, it will be 3 edges. And we power it up. This R will be a parameter that depends on epsilon. So this is a product graph, right? So if you take an edge, you get a hypercube. If you take what we have, which is a path of length 3, we are going to get some grid. And then you take the outer product with the original instance. I mean the product graph with the original instance. And then we have to do some smoothing. So it just means that you add some edges to exclude some bad events. Okay. Now, once you do this, claim is that if the original SSE instance had small set expansion less than epsilon, then the vertex expansion of your new big graph will be less than epsilon prime. And if the small set expansion was large, then in fact the vertex expansion is larger by a much bigger factor. Okay. There is a big gap here. There is some gap here. So the gadget is this. This small graph H is just this, with weights on the vertices. You power it to the R. And there is this notion of, okay, so we have to argue about cuts, right? We have to argue that if there is a small set with small expansion, it's preserved. That's relatively easy. Basically, forget about the graph G0, the instance. Let's just focus on this product graph. Turns out that the technical difficulty of proving that this reduction has these properties is to actually prove properties of the product of this tiny graph. And what you want to show is that if you take a subset of vertices of the product graph, so that you are taking all copies of some vertex. Okay, so this is a dictator cut. Like if you have a hypercube, you're taking cutting along a dimension. Then in fact you have small expansion. I mean that's the point of this, right? If you cut here, here, or here, it's small, and this remains the case even if you make a product graph. But if you cut in any way that's sufficiently far, and we have to define what sufficiently far is, then the expansion is huge. This is a combinatorial claim.
Where's D?
D will show up in D is already there in how we power this up. I mean, this power determines the degree here, and yeah. So it's just an example with H being a single edge, cube. And basically the difficulty is to try to show that for all subsets which are far from axis cuts, the expansion is large. D is now the number of times. Basically D is large. Now, how do you prove this combinatorially? These combinatorial things even on hypercubes are extremely difficult. So for this we have a nice path laid out, which is to say that look, the quantity you're trying to estimate is actually very close to what you would get if you replaced your distribution on the graph with a continuous Gaussian distribution. And then we get a question about Gaussians, and maybe that's easier to answer. So again, this is just a sketch of what I said. You need to show every subset far from the dictator has high analytic expansion. For this, you show that in fact it's sufficient to prove it for subsets of a Gaussian graph, which we'll define in a minute. And this is what I was saying. This is the function with some Boolean inputs, which is whether an edge is present or not. And this is where we are adding some noise, meaning some random edges to smooth out. But the key step here is that you're replacing Boolean with Gaussian. I won't try to summarize a lot of work in more than this, but okay. So for us, this will be the analytic vertex expansion of the gadget, the powered up gadget, and this will be the analytic vertex expansion of a Gaussian graph. So what's this Gaussian graph we're talking about? It's the vertex set is all of Rn, and the weight on an edge is proportional to the Gaussian density. And so if you centered at one of the nodes and you looked at how much Gaussian weight you get at the other node, that with variance epsilon. Now, yeah, you can also think of it as the density that you get x is u and y is v for two correlated Gaussians. So, and then you can ask, what is the analytic expansion of this Gaussian graph? For any subset, if you look at this function which picks neighbors, and so what is this question? So let me make this question precise. You have this Gaussian graph, right? So it says Rn and your weights on all pairs. It's a complete graph with weights, right? And now you ask, I take a subset, I pick a vertex at random, and I pick d neighbors according to the edges, and ask, is there at least one outside my subset? Right? Because if there's at least one, you want to count. So what's the probability that when I pick a random vertex from the subset and I pick d neighbors, at least one falls outside? Normally you just ask, if I pick a random vertex and a random neighbor, what's the probability that it's outside? So we're asking this in the continuous setting, and the theorem is that in fact if this epsilon correlated, the epsilon is this correlation parameter, then you get square root epsilon log d. Okay, so the proof of this is completely geometric. You have a Gaussian, and you can reduce the question to the one-dimensional case. Sorry, ignore the comment. So I have some subset. I'm picking a vertex from it, subset S, and I want to know, if I pick d neighbors according to this distribution, what's the probability that one of them falls outside? Okay. So in the proof of square root opt being a lower bound for regular edge expansion, it's the same question with d equal to 1. What is the isoperimetry of the Gaussian graph? And there, the answer is square root epsilon. Here, it's a slightly more complicated question. You're picking d neighbors. What's the probability that one of them falls outside? So here, the proof really is one slide. So here is a subset. Everything on this side is a subset you are in. Let me define two other subsets. One, which are kind of deep inside. Okay. In what sense are they deep inside? This S1 is a subset of all points. Okay. So that the probability that when I take a point here and a neighbor, the probability that it crosses is less than 1 over 2d. Okay, so there's some threshold here. And I'm saying, I want to fix this subset so that the probability that it crosses is less than 1 over 2d. Okay. So, of course, as I make this threshold smaller and smaller, this will be a smaller and smaller subset. Okay. Now, by simple Gaussian geometry, if you have two vertices whose distance is small, then if you take one Gaussian neighbor from them, then in fact, if you apply Gaussian centered, if you consider a Gaussian centered at those points and they're close enough, the distributions overlap a lot. Okay. And therefore, if I now make these so therefore these subsets, since they have very little probability of crossing over, must be far. Because if they were closer, they would have a probability 1 over 2d of crossing over. But I said they don't, they have a very small probability, so they must be far. And in fact, the distance is square root epsilon log d. So that's sorry, it's too rushed right now, but that's so in conclusion, distinguishing whether a graph has a vertex expansion less than epsilon 0 or at least 0.1 is the problem, and as far as we can tell, this is hard if you believe the SSE. So this is a summary of the sort of the algorithmic approximation bounds on this problem. So there's latent row, square root log n for the two problems. And then this came earlier, but since it's different, I put it here. And then this is what the simple SDP gives us. It's also known, this is the strongest result we know, assuming the exponential time hypothesis, there is no p-test for these problems. And this is what RST proved, that square root opt holds for edge expansion, which implies also for vertex expansion. And this is what we just saw. That square root opt log d is a lower bound. Here are some questions. Of course, better approximation, right? In a sense. I love this algorithm. So maybe you've seen it. I first heard it from Gary Miller. He says following. Cheeger says take the Laplacian, take the second eigenvector, sort it, and consider the n-1 cuts, take the best. Gary says take all the n-1 vectors, sort all of them, sort the vertex on all of them, consider all the n-1 cuts from each of them, so you get about n squared cuts, take the best of those. Okay. The worst known example for this is square root log n. But we don't know how to prove better than square root opt. So I guess show that this problem is actually NP hard, the expansion problem, not SSE, the 2n 1.01. Finally, this process that I mentioned, one difference from a random walk is that we don't know how to do this implemented locally. So for a random walk, you just need to know the current vertex, and you keep moving, and that's all you need to remember, the identity of the current vertex. This one, as far as you can tell, you have to keep track of the entire distribution to update it. So is there some local implementation of this? Then the process could have applications to other things. That's it.
Questions?
So for the dispersion process, I guess one thing that makes it hard is the max, but are there variants of it that don't use it that could give similar results? Like
I don't know. So instead of the 2 norm, you could try a different norm, for example. Instead of summing up the squares, you could sum up the square root of the 4th powers and so on. All seem to give weaker results without having a natural. The sum of squares, great. A polynomial time, random walk, everything is great. Any other norm, I don't see an advantage. This one gives the best bound we know of. So, no, I don't know. Yeah.
So if you could find a fixed point of your diffusion process, so then that Rayleigh quotient like expression will give you gamma 2. And then gamma 2 gives you root of the approximation for the hypergraph expansion. And so then that gives you a solution to small set expansion.
Yes.
So that must mean that
computing gamma 2.
That finding that fixed point should be hard.
Yes, at least under SSE. Yes.
Yeah.
This is what I was saying, that it's going to be hard in this sense, but no, I don't know if yeah, that's right. Yeah. Yeah. So
but since SSE you said it's kind of ridiculous anyway.
Well, I was trying to.
It's more ridiculous than your Niguez conjecture.
Yeah.
Yeah, I said ridiculous only to wake up people.
Yeah.
Obviously, it's interesting because it's leading to lots of questions.
But do you have a sense that, in fact, there are cases where the convergence time is exponential for your diffusion process?
I mean, Anand is also here. I don't know if Prasad is here, but do we have exponential time lower bounds for?
The thing is that you can always find a fixed point. Just that you will not be able to certify that it is the one corresponding to the smallest one. So if you
He's asking, can it be exponentially small, the gamma 2?
Yeah, I mean, in the same reason, right? For as the spectral gap of a graph can be exponentially small. If you have a weighted graph, it can
depending on the weights. But let's say it's unweighted. Let's say it's weights, of course. But
if it's unweighted, then Cheeger's inequality shows that it is lower bounded by 1 over poly n.
Yes.
Oh yeah, 1 over poly n.
But you said that there is many maybe there is exponential number of fixed points, and you'll find the bad one. That's the kind of.
No, every fixed point will give you gamma 2.
Yes.
I mean, there's a unique fixed point.
That's right. That's right. Under this very mild, exactly. Yes, that's the point.
So we'll keep discussing.
Yeah, just maybe in the interest of time, like, we can probably continue this conversation over dinner or yeah. Good. So let's thank Santosh.